All right, everyone. Can you all hear me, see me okay?
Yes, sir.
Yes, we can.
That's weird. I just got like the blue screen of death. Weird. All I did was started writing on my screen and I got this strange crash of the system.
That's terrifying.
Oh, well. Give me a minute to just get everything back up. Okay, that should do it. We are recording. Everything looks like it's back. Let's see what happens when I write on my screen. We're still here, okay. Okay, so I thought I'd start class today by just doing a quick review of the things that we've done up to this point. Obviously, we started this whole thing out with finding the area under a curve. When we did that, we were just assuming that y was a function of x, and we came up with the basic definite integral. That was our first step into this. And then we said, okay, what if we have two curves and we want to find the area between them, and both of those curves are functions of x? Then we can figure out what our limits of integration are. Sometimes those limits of integration will be given to you. Sometimes they'll be the intersection of two curves. It just really depends on the problem. But the whole idea here was that we'd be finding a formula for the area of a single rectangle, which would be our top curve minus our bottom curve times the width of each rectangle, and then we add them all up. So we bring the integral in. And then if we have two functions of y, well, we can do everything the same way, except we turn our rectangle sideways, and we find the area of that little rectangle, which would be the curve to the right minus the curve to the left, times the width of the rectangle, which is dy, and we integrate from c to d, which are these restrictions on our y values. So is everyone clear with these three concepts? Anything that you need clarification on? We're okay? All right, then last class we talked about our first kind of introduction into this idea of volumes of solids of revolution. And we started with this idea of taking some region that's bounded by two curves, in this case, two functions of x, and taking the rectangle over here to the side, rotating it around the x-axis. And when we do that, we get this washer, and we had come up with a formula for a washer before we even started all this. And we said, well, the two things you really need to know are the distance from here to here, which we called r out, it's our outer radius, and then distance from here to here, which we call our r in. So I want to be very specific and make sure that you understand there's something important in terms of where we're headed with this. When we talk about r out, we are always referring to the distance from the axis of rotation to the outer edge. Outer, is it two T's? Outer edge? Is outer two T's? No, right? I don't know. I don't really care, actually. And then the inner radius is the distance from the axis of rotation, same thing, to the inner edge. And when I say edge, I'm talking about the edge of the rectangle. So that's why normally when we rotate around the x-axis, this outer edge, this outer radius is always going to be the curve that's on top, okay, which would be whatever that blue curve is. And the inner radius will just be the curve that's on the bottom. But that's only if we're rotating around the x-axis, because the distance from the x-axis to the two curves are those curves values, the function's values. As you're about to see, this could change. The outer radius and inner radius could be something different. So just want to be clear that it's always something we have to look at, the distance from the axis of rotation to that outer edge. Okay, now, now what we're going to do is we're going to, wondering if we should do an example to start. Let's just do an example. We all had a good weekend, right? So let's find the volume of the solid generated by revolving, oops, the region bounded by, I'm just going to write these in here. Let me see. I had this earlier. It's gone now. Let's just do something pretty simple to start off. Y equals x squared and y equals 4 minus x squared. We'll do 8. Sorry, 8 minus x squared. Make things work out a little bit nicer for us. And then I have one more thing with x being greater than or equal to 0. Okay, so we want to find the volume of the solid generated by revolving the region bounded by these curves in this condition about the x-axis. I need to state that here. About the x-axis. All right, so first things first, we've got to get an idea of what this looks like, right? So I go to my graph. I have y equals x squared. We all know that that's just a parabola that opens up. And then we have the other one, 8 minus x squared, which is a parabola that opens down and intersects the blue curve, and it's up here at 8, right? So that's our general shape. So there's a region. We have this whole region, but we have this additional condition that x has to be greater than or equal to 0, which means we are only looking at this part right here. Now, I chose to do that because of what we're going to do in a little while. I want to make sure that we're not on the other side of the y-axis. Okay, so we want that region. We want to wrap it around the x-axis, and we want to see what volume we would get. So what I do now, what I like to do is I like to make sure I show here on my graph my axis of rotation. So I draw little circular arrows. I like to.
Question.
Yes.
So whenever we are finding the volume, is it always left to right? And when shear area, it's up and down?
Always left to right? I'm not sure what you mean left to
Yeah,
right.
I mean the rectangle, like, or it doesn't matter, because I was doing the problems for 7.1 and there were questions in which I had to find the area using the left and right property of a rectangular.
It depends the function, I think.
Yeah. So look, first of all, 7.1 was areas, so that's kind of different. But in terms of that, yes, if they are functions of y, not functions of x, then we would have our rectangle go sideways, right? Right now, what we're doing is we're trying to take a region and wrap it around the x-axis. So right now, if I do vertical rectangle, see, if I do a vertical rectangle, this makes sense because the function on top and the function on the bottom are different functions, right? So the thing that's dictating the top edge and the bottom edge are different functions, right? So this is very much like finding area, except our formula is going to be different. I don't know if that's addressing your question.
Yes, I understand that.
Don't worry, don't worry. We're about to turn these things sideways, all right? We are going to have to do that, but one step at a time. So we have this, I draw my little circle, I draw a rectangle, and then this is where I said I like to draw my rectangle to the side, and you will see today why I like to do this. I like to put my x-axis. I also like to put my axis of rotation, which I'm going to do it in orange, but it's also the x-axis, so they're in the same place. I also like to kind of show, let's see, the green one is on top and the blue one's on the bottom, right? I know that the distance from here to here is my R out. And what is my R out in this case? What's my outer radius, that distance from the axis of rotation to here? For this specific problem, that's what?
8 minus x squared.
Minus x squared, good. And then for the inner radius, which is from here to here, that's the other curve, that's x squared, right?
Mhm.
Now, I don't care on the rest of, like, if you're doing this work on a test, I don't care for more pictures. If you want to, you can draw more pictures. You can draw me what one of these washers looks like. You could label it, you know, you could show me your axis of rotation. You could show me the R out. You can do all that, or this is good enough. Okay, this is fine. We still need to resolve our limits of integration though. We still need to see where we start and where we stop. So hopefully it's obvious that we start at 0 because it told us to be to the right of 0, but we still need to figure out where they hit each other. So I've got to do a quick intersection. I need to figure out where x squared equals 8 minus x squared. So this should be pretty straightforward. We'll just move the x squareds to one side, divide by 2, and we get 2 answers, plus or minus 2, and we take the square root. I'm going to throw away the -2, right? Because I'm not allowed to go over there. So I know that this happens at 2. And that's it. We have everything we need to set this integral up. The formula is pi integral 0 to 2, outer radius squared, that's the outer radius, that's 8 minus x squared, squared, minus the inner radius, which is x squared, squared dx. Does everyone see that? And everyone remembers that the whole idea came from this pi r out squared minus r. Well, you know, I can just show it to you. It all came from, come here. When we were looking at the volume of a washer, right? When we were looking at this washer, stop it. And it does not want to cooperate. When we were looking at the volume of this washer, we were talking about, you know, it's the volume of a cylinder, and then you take out the volume of the other cylinder, and we came up with this formula right here. And that's what we're basing everything on, right? Okay, so that's it. At this point, you could do this integral, right? You just square that, so you'd FOIL it out, and you collect all your like terms, and then you just integrate power rule. This should be a pretty straightforward integration, okay? Any questions? All right. So now, let's do a problem very similar to this. All right, so I'm going to actually take this. I'm going to erase some of that so I can grab it.
So, Professor, on the exam, you would require us to give you that area, that number, right? Once we take the integrals of each r out minus r in.
Well, on this right here, on the test, you'll have to do at least one integral where you have to do it the whole way. Now, it might be an area problem, not a volume problem. It might be, you know, where you're finding the area between two curves. That it might be that. But we are most likely with these volumes, I'm not going to ask you to compute them, which means it's extremely important that you get it set up properly. Because if you don't set it up properly, it's wrong. Then you know
Everything's wrong.
Yeah. So this is all about taking the geometry and turning it into the math, and then the math we know we can handle that if we had enough time.
So we're only going to get it to this form where we match the formula. That's it.
Yes. Yes. On the test, you will.
On the test.
What I'll be. I mean, it wouldn't hurt you to do it on your own, but. Okay, so I'm going to change this problem just a little bit. So I'm going to copy it, start a new one.
Can we also get your notes from this class, Professor?
Yes, I'll send those to you in the chat.
Mhm.
Okay. So I'm going to change things up. I want to find the volume of the region. Okay, but this time I want it to be x equals y squared. Okay, I want it to be x equals 8 minus y squared. And I want it to be for y greater than or equal to 0. And I don't want it around the x-axis. I want it around the y-axis. So I changed that x-axis to y-axis right there. So again, I'd go through the same procedure. I would go and graph it. Okay, x equals y squared. That one I'll do in blue. That is a parabola that opens sideways like this. And then the other one I'll do in, I guess, red. That'll be a parabola that starts at an x value of 8 and opens up this way. Do y'all see that's basically the same exact problem, just laid sideways? Right?
Mhm.
And then y being greater than or equal to 0 puts us up here. So we want to wrap that around the y-axis. So I'm going to draw my axis of rotation here with the little circular arrows like that. Okay, here's my axis of rotation. So here's the thing, we cannot use vertical rectangles anymore. Look, if I do a vertical rectangle, then I'm supposed to wrap that around the x-axis to create the washer, right? But we don't want that. We want it actually to be the other way around. We want to wrap this thing around the y-axis. So it makes sense for us to draw a rectangle this way instead, and then wrap it around, right? Wrap it around. So I'm going to do the same thing I did before. I'm going to draw below this. I'm going to draw my y-axis. Instead of out to the right, I'm going to do it below. I'm going to draw my rectangle that I'm wrapping. I'm going to draw my axis of rotation. I'll draw that in orange. Here's my axis of rotation. And so hopefully you can kind of imagine that if I were to wrap that around the y-axis, I would get a washer, a more traditional washer, right? That's kind of laying flat. That's what would happen if I wrap that rectangle. Now, I do know that the right edge of that rectangle is there. That's the red curve. And then I know that the left edge of the rectangle is here, but I still have the same concept of an outer radius and an inner radius. It's just now they're functions of y, not functions of x, right? So my outer radius should be the red one, should be that one. My inner radius should be this one. And that pretty much allows me to set up the integral. I just need the limits of integration, right?
So it's basically the same when we were doing the right side of the function would be the outer radius here.
Yeah, it's like the right side's the outer, the left side's the inner.
Yeah.
But that's only because we're wrapping it around the y-axis.
Yes.
Okay. All right. So I know I can go integral, I know pi, I know my outer radius squared. So that's the outer radius, square it, minus the inner radius, which is y squared, and I'm integrating with respect to y this time. And then I need my limits of integration. And you could do the same algebra. I mean, this is exactly the same algebra. You should get 0 and 2. Okay, so it hits up here at 2. So what's the moral of the story is this. If you've got functions of x and you want to, so that's the previous problem. I'll leave this up here, but if you have functions of x and we're wrapping around the x-axis, then everything's the way you would expect it to be. But if it's functions of y going around the y-axis, then you've got to switch everything up in terms of y, but it's still washers, right? Are y'all agreeing with this? This is still washers. Anytime we wrap the rectangle, we get a washer. Whether the washer be sideways or vertical, we're still getting a bunch of washers and adding them up. Okay. With that all said, I think we're ready to...
One last thing, Professor, how do we set the limits on this?
Same way, you would have to say, well, first of all, we're talking about the limits of integration are your restrictions on the y values, right? Not the x values.
Mm-hmm. Oh, so setting the equations together, right?
Yeah, you're setting y squared equal to 8 minus y squared.
Okay.
Yeah. Okay. Now, I want to go back to the original problem. Okay, here's the first problem I gave you. And I want to change something now. I don't want to wrap around the x-axis anymore. Here's what I want to do. I want to wrap it around this line, y equals -4. Okay, so we all need to know what y equals -4 looks like, but I'm going to just start from the beginning here, draw my graph. Now this is the third time we've graphed these, so this x equals y squared's in blue. The 8 minus x squared, that's in green. I'm still to the right of 0, or to the right of the y-axis. And now my axis of rotation, okay, y equals -4. That's actually down here. Here's -4. My axis of rotation, I like to draw it as a dotted line. I haven't been drawing it dotted because the x-axis has been in my way. But now I'm rotating around that. So first, let's all agree on something. When you wrap this around that line, -4, y equals -4, do you agree that you would get a different solid than if you wrapped it around the x-axis? So like if you just wrap this around the x-axis, imagine wrapping that around the x-axis, you would have something that looks like that. It would actually look like that, but it would have like a point in the back. So in other words, if you wrap this yellow region around just the x-axis, it would be closed off. Like the whole front of the solid, the whole front of the solid would be a solid piece. There would be no hole in it. Do you all agree with that?
Yes.
Yes. But if you wrap it around this line, it's got to go all the way around. I guess you could do it this way. See if this will work. So if I have, this may not work. If I have, this is a pin. I know it's hard to see. I have a pin, I have this little thing. If I wrap this, if it's touching the x-axis and I wrap around, I'm going to get a solid, right? And that solid is going to be pretty small. But if I move my axis of rotation down and now wrap it, it's got to go around all this, and it leaves a big space in the middle, doesn't it? So that solid looks more like, it's harder to draw.
A more space in the washer then?
Yeah. You actually would have a hole in it. Like if I do this yellow around this orange line, I'm going to have a hole in the center of it. As opposed to if I just wrap around the x-axis, it's going to have no hole in the center. It'll have a little bit of hole in the back, but it won't go all the way through. Do you all see that those are completely different objects? And so that they should have completely different volumes. So
Yes.
we have to account for that somehow. So here's where drawing the picture, I think, becomes vital. So I was drawing my rectangle in here. And then what I like to do is I like to draw that rectangle out to the side. I like to label the x-axis. I like to put my axis of rotation down here. I'm also going to remember that the top part of this rectangle is the green curve. The bottom of the rectangle is the blue curve. And now I need to just find the outer and inner radius, right? The outer radius is the distance from the axis of rotation to the outer edge of the rectangle. That means the outer radius is this distance all the way down. That's R out. And R in is from the axis of rotation all the way to the bottom edge of the rectangle. Do y'all see that these measurements here, these distances are much different than here in the first problem we did? Here it was just our axis of rotation was the x-axis, so R out was just here, R in was just here, but now.
Professor, would you say that that would be a much bigger washer than the one that actually rotates on the axis?
Absolutely. Each washer has a bigger radius. So that each washer is bigger, so the volume is going to be bigger.
Okay.
Now,
But in terms of how we calculate seems to be the same, right?
yeah, I mean, we're going to be using the same formula the whole time. But we need to now think about what the outer radius is going to be. All right, this is the important part. We know that from here to here, okay, from the top edge of the rectangle to the x-axis, that alone is the 8 minus x squared, right?
Mhm.
But we need to go a little bit further. We need to go this distance that much more, don't we? How much is that distance?
X squared.
No,
Minus
How
4,
many-
-4.
like if you got a tape measure
It's
out.
R in. No,
No,
No, it's 4 because it's from the origin, isn't it?
that's right. So from here to here is just how far down that line is. And that line was what, -4? But we're looking at it like a measuring tape. So we're measuring 4 units. So this right here is 4, right? So we have from here to here is 4, plus we have this much, which is the function's value. So our outer radius, I'm just going to write it down here, is the 4 plus the outer the function that gave us the top of the rectangle. So when we put all that together, we get 12 minus x squared. So all I did there really was added the number 4 to the curve.
Right. So we have to be careful not to put in the negative because it's adding on to the radius, not subtracting from it.
That's right. We want to look at that as a distance, as like an absolute value. And so that way it's accounted for as a distance whenever we calculate. Now, the inner radius is going to be very similar to what we just did. We have the distance from here to here, which is 4, but then the distance from here to here, which we know is the bottom curve, which is just x squared. You all see that? From here to here is 4, from here to here is x squared.
X
So
squared
the
plus
inner
one.
radius will be those two added, 4 plus x squared. The limits of integration, we already got those, right? 0 to 2. So we can just crank it out. It's the integral, don't forget the pi. 0 to 2. It's the outer radius, which is 12 minus x squared, minus the inner radius, which is 4 plus x squared, but that quantity squared, dx. And that's it. I mean, we would have to square this all out and expand it and collect like terms, integrate, power rule, we'd be in business, right? Okay. So that was an example where we took a region, we rotated around a line that was below the region that we were talking about. Let's look at a different example.
Random question.
Yes,
So, could you go back to that other one? The first
I
that
will.
we were just on?
Yep.
Okay. Well, my question was, yeah, what if y wasn't equal to -4? What if it was equal to -4 minus cosine x? Could you, and then you tried to rotate it around that? Would that lead to issues or?
okay, so,
So basically, if it wasn't a straight line.
okay, yeah, so in this class, we will only rotate around lines that are horizontal or vertical, all right? We will never try and rotate around a line that has any slant to it. Is it possible? Yes, but it's not for this class, okay? That's a different class because you have to be able to do rotations of the entire, you basically take the entire two-dimensional space and transform it. So you do a rotation of the whole space, which means you have to use matrices to do transformations. that's not in this class. That's beyond the scope of this class. And we will never rotate over anything that's non-linear, because if you have like a curve, like let's say you had a sine function or cosine, like you said, like then your radius is changing with respect to not only the curves up at the top, but they're changing with the curves on the bottom also. And in all practicality, doing something like that doesn't translate into the real world. Like there's not a problem in the real world where your axis of rotation needs to be something other than a line. I mean, most of the geometric shapes we are getting when we rotate are things that you could find in the real world. Whereas if you try and rotate along something that's nonlinear, you're going to get some shape that you probably can't even represent in the real world, if that makes sense. Yeah, it would be an interesting mathematical problem for a pure mathematician. Would be like, okay, so how would that adjust the formula? But it's not practical for what we're going to be doing. Good question.
All right, yeah, just random thought. Okay, thank you.
No, good. I'd keep asking. Okay, so now what I'm going to do is I'm going to change it again. We're not going to go around the x-axis. We're not going to go around y equals -4. Let's go around y equals, I don't know, 15. So that's another horizontal line, isn't it? But this time, where is it?
Top of the x-axis positive.
It's way up above our region, isn't it? So we've got the x squared here. We've got the 8 minus x squared here. We're still just looking at the right half, like that. And our axis of rotation this time is up here at 15. I should also point out, not only will our axis of rotation always be horizontal or vertical lines, the axis of rotation will never go through the middle of our region. It will always be outside of the region, because that would be kind of strange to rotate around a line that's within the region that you're talking about, because it would basically create a double volume, and we won't get into it, but that's what would happen. Okay, so you all see this? You all got this? Okay, my axis of rotation is up here, right? So I'm going to do everything I've been doing. I'm going to draw a little rectangle. I'm going to move my little rectangle off to the side so I can isolate it. I'm going to draw my x-axis. Very important that I'm about to draw my x-axis. My axis of rotation's way up here. I know that the top edge is the green. I know that the bottom edge is the blue. Now, let's talk about R out and R in. R out is the distance from where to where?
Are out from the axis that it's spinning to the outer edge.
To the outer edge. That means we're talking about this. I like to look at it like, here's a person, okay? That's their head, there's their arms, okay? We're looking from the top straight down, and that's the little person's head. He's looking out this way, and he sees the rectangle laying out there on the ground. And what we're talking about is the distance from that person to the outside edge of the rectangle, which is there. Because you have to imagine that this thing's going to be spun this way, right? It's not going around, it's not going around this axis anymore. It's going around this. So this thing's getting wrapped around, and it's going to create a washer up here, right? So the outer edge is actually this edge, not the edge that's always been the outer, right? The outer's always been this one because our axis of rotation was down here, but now their axis of rotation is up here. The outer edge is this one. Understand? Anyone have a question on that? So this is R out, and this would be our R in, the distance from the axis of rotation to the inside of the rectangle. Now we need to figure out what R out is. So can someone tell me what the outer radius is?
X squared plus 50.
Do you have to,
Close, not quite. Look, this right here, from here to here is x squared. Agreed? That's x squared.
Mhm.
And then, from here to here is the 8 minus x squared. Right? So just for the sake of making this easier for everyone, let's say that this distance from here to here, let's just say for example, that distance was 2. Then what would be the distance from here to here?
17?
Mm,
13, sorry, 13.
13, because the distance from the axis of rotation all the way down, right, is 15. So if this were 2, then what the distance that would be left would be 13, right? If this right here was 5, then this would be 10. If this right here were 10, then that would be 5, right? So what is that mathematical computation that you have to do to figure out what R out is?
You subtract.
Subtract 15.
15 minus x squared.
15 minus the x squared. That's what gives you the outer radius. So it's not 15 plus x squared, right? It's 15 take away the x squared. With that similar sort of logic, what would Rn be?
Then 7 minus 8 minus x squared.
Where are you getting 7 from?
Since 8, we know that the inner edge is going up till 8, and then there's 15. So 15 minus 8 is 7.
No,
Yeah, but this is not always 8. This right here is not always 8. That always depends on x, right?
It'd be 15 minus 8 minus x squared.
Yeah, it's
In, like,
15
parentheses.
minus 8 minus x squared. See, we don't know what 8 minus x squared is, but whatever it is, we have to take that away from 15 and that'll give us what remains.
Okay.
Does that make sense?
Yeah.
Now I can clean that one up a little bit. That's going to be 7 plus x squared. That's what that is when I put that together, right? 15 take away 8, then minus minus is plus. Everything else is the same. So the integral becomes pi. We're still going from 0 to 2. We're still going to do the outer radius, which is 15 minus x squared minus the inner radius, which is 7 plus x squared dx. These problems, these solids of revolution, are the types of problems that Wolfram Alpha and all those websites, like, they can't help you on these yet. Like, technology hasn't gotten to that point yet where you can just type in this problem and it gives you the integral. You can type in an integral and it'll give you the answer, but it can't translate this problem into the integral. So you really have to understand the geometry here in order to be able to come up with the correct answer. Any questions? Sure. Okay. So let's just for fun here, let's break out an old test of mine. See what kind of things I asked on this. I can probably see what I did.
Do you think we'll be able to cover all of these topics in time? Because today we were supposed to start sequences in terms of the syllabus.
Yeah, no, we will probably not get to the chapter 9. But that's pretty normal. I mean, I normally don't get to chapter 9. And so what I do is I just tell my students, hey, I've got YouTube videos on chapter 9. If you want to watch them, watch them. The chapter 9 stuff's not that hard. It's actually much easier than chapter 8. But we have to get through chapter 8. Okay, so look, this is an old test. So I gave them an improper integral to start, so I must have not tested them on that. Find the area of the region bounded by these functions, and then write your answer as a decimal. So I made them actually calculate that whole thing. So that's the area between two regions. Then I said, set up the integrals, but do not evaluate them, which give the volume of the solid form by revolving the region bounded by, and I gave them the region here. And I had them revolve that around the x-axis, y equals -3, y equals 4, the y-axis, x equals 5, and x equals -3. So they had to generate here 6 different integrals because I had them rotated around 6 different lines. What we've covered so far would cover us for the first 3. So the idea is that on a test, what I'm going to do is I'm going to give you a region, right? This region, I'm going to have you rotate it around the x-axis, a line down here and a line up here. That makes sense? And then I'm going to have you rotate it around the y-axis, a line over here and a line over here. Now we haven't done that yet. Okay, we haven't done that. We haven't seen what it's like to rotate around the y-axis yet. I mean, we did, but that was in an example where we just changed all the variables. So let's get to that. All right, let's actually contemplate that.
Isn't the general concept the same?
It unfortunately is not. Okay, so let me show you why. All right, let me show you why. And this is going to require we introduce something brand new. It's going to be badass. You're going to love it. Okay, so let's consider this. Let's say we have a region that looks like this. I'm going to make it look like this. Here we go. We got this region or that curve, and you have that curve right there. So there's our region. Now, if I asked you right now to take that and wrap it around the x-axis, everyone should be in business. All right. If I gave you, said, hey, wrap it around there, you should be all happy about that. Not happy, but you should be able to handle it. If I gave you this line, say wrap it around there, you're gonna be like, yep, I can do that. If I give you a line up here, you should be like, oh, yep, I've got that. We just did a problem like that, right? But what if we try and wrap it around, let's just say the y-axis. So what if we try and wrap it around here? Does anyone see why we can't just switch everything over to horizontal rectangles?
Because it's a function of y, or
They're not functions of y, right? So if I'm going to try and do this rectangle like that and wrap around the y-axis, I run into the problem where the curve on the left and the curve on the right are the same curves. So I can't do it. Does that make sense? Now, that was not a problem when we were doing areas, because when we were doing areas, I could find the area of that yellow region. I can do it. Regardless of what it is, I can do the area of that. I can do the area of this, like if I reverse it. So if we're talking about areas, we can find the area of the one on the left by doing vertical rectangles. I can find the area of the one on the right by doing horizontal rectangles. But if I'm trying to wrap around the y-axis, I don't get that choice because I need my rectangles to go this way so I can wrap and get a washer. Is that clear? So you can't just switch things up, but we have a workaround, okay? We're gonna be able to solve this. And here's what it's gonna require.
Can we just rotate it around the same principle, like in a way, like a vertical rectangle and then rotate it?
That's exactly what we're gonna do. That's exactly what we're gonna do. We're gonna do a vertical rectangle. We have to, we have no other choice, okay? We have to use a vertical rectangle and we're gonna wrap it around. But when you wrap that around the y-axis, it's no longer a washer. It's something else, all right? So what would that shape look like? I don't know, maybe you can visualize what this whole thing wrapped around this whole thing would be. Do y'all
Like a
see this?
cylinder with a huge hole in the middle.
Yeah,
A tube.
it would be like a tube. Yeah, a tube. like almost like a garden hose that you've cut a section of garden hose out. Do y'all see that? That's what would happen if we wrap that around. And this is what we call a shell. All right, that's called a shell. So we've been dealing with washers, and now we're looking at this idea of a shell. Just like before, if we can come up with a formula for one of these shells, then we can use the integral to add them up. So I have an illustration to help us see this. I think it's this one. Yeah.
So we no longer have a washer now.
No, we do not. That's correct. Okay, here it comes. This is not a really great animation. Okay. It's not a great animation, but it's decent. So what we're doing is we're taking our curve. So I don't know if you can see this, a blue curve. We're trying to wrap it around the y-axis. So what we do is we cut it into a bunch of rectangles. Man, this thing is slow. Oh, let me evaluate this again. Okay, so we cut it into a bunch of rectangles. And we wrap those around the y-axis. Okay, that's what I meant to put. This thing really doesn't like this. But do y'all see these? They come all the way around, all right? But that's just to show you that we get all these shells, and then we just put an infinite number of them in there. Okay, let me see. I lost all of y'all. Where are y'all? There you go. Okay. So can we come up with a formula for the volume of this shell? Well, do we know anything about this shell? Do we know how tall it is? How tall is this shell? Remember, it came off this rectangle, right?
The max and min points. Local max, local min.
Well,
Just the
the
top
shell's
function,
going
not-
to change. As we move through, the shell's going to be in a different place, right?
It's just a
Right.
top function, right?
Top. The top.
minus bottom.
Top minus bottom. This is just top minus bottom, isn't it? That's all that is. The height of the rectangle is just the top one minus the bottom one. Okay. Well, that helps a little bit, but it doesn't really help me get the volume. Because to do the volume, don't I need like an inner radius and outer radius?
Mhm.
Right? Okay, so we're gonna do something clever here. Imagine that if you could come in here and cut this cylinder. Okay, if you had a pair of scissors, or not cylinder, if you could cut this shell, all right? Cut it and lay it out flat. Okay, imagine me cutting that and laying it out flat. Do you all see that this would become something like this? Right? Cut it along the red line and lay it down on a table. And you'd have that, right? Now you have a box. And the volume of a box is length times width times height. We know the height we just said is the top one minus the bottom. Do we know how thick this is? How thick is this shell? Where did the thickness of this come from?
dx.
Yeah, it came from the thickness of the rectangle, which has always been dx for us, right? Hasn't that always been dx? So we know it's dx thick. How long is it though? This is the hardest part. How long is this shell? So let me illustrate with the
2 pi.
Close, yes. This is a shell, right? This is a shell. We cut it and then we opened it up and laid it flat. The distance from here to here is also the circumference of this thing.
2 pi
isn't it?
r.
2 pi times the radius. Yes?
Yes.
So 2 pi times the radius. Now, 2 pi I can put here, fine, that's 2 pi, but what's the radius? I'm gonna put that R and I'm gonna highlight it because I'm not quite sure what the radius is.
It's H.
The radius is the distance from the center to the outer edge, right?
Mhm.
But that distance, let me see, on my graph, isn't that the distance from the axis of rotation to my rectangle? Isn't it this distance? Like it depends on where my rectangle is. Like my rectangle's here, then the radius will be this. If my rectangle's one of these other ones, right? Then my radius is gonna be a little smaller, won't it?
Yep.
Okay, so it's important to know that, and I think I'm gonna draw this below this. It's important to know this, that when we've been doing this, and we've had these rectangles, these vertical rectangles in here, when we've done our integral from A to B, dx, and let's not even worry about the integram. When you're saying from A to B, what you're saying is that you're going to start at A and you're going to end at B, and you're going to start sliding these rectangles across the region, right? So they just start moving along. So if I pick some arbitrary point and stop it and say, hey, let's look at that rectangle right there, the distance from the y-axis to that rectangle is always going to be x. Because what is x going between? X is going between A and B, right? So it's going to start, x will start here, x will go, get bigger and bigger, and x will stop at B. So x is always the distance from the y-axis to the rectangle. And in this case, isn't that the radius we're talking about? Isn't that what this is? It's a distance from here to that rectangle, which for us here would be x.
So the distance could be anywhere between y-axis to the rectangle in the curve anywhere.
It can be any, it can be between A and B, but it's a variable. It's the variable x. Okay?
Okay, yeah.
It's always going to be x. Hold on a second. What's up? Okay. Okay. Yeah, Cora, I'm in the middle of class. Kids, man. All right, so we've got to put together the formula, right? The volume of this thing, right? We want the volume of one of these. Should be length times width times height. So it's 2 pi x times top minus bottom times dx. So that's just all these multiplied, 2 pi x times that times that. But we want to add them all up, right? We want to add them all up. So we want an integral. And our integral is going to go from A to B. Because remember, that's what x is going to slide between A and B. The 2 pi can come outside. I have the x is still in there. And then I have top minus bottom. Dx. And that's the one that you need. Well, I'm going to say circle that, but I'm also going to have you put question marks on that because that's not the final version that I'm going to give you. But that's pretty close to what we need for right now. I say we do an example. Yeah? Let's do an example. Not this one, I have to change it. Okay, so find the volume of the solid generated by revolving the region bounded by, here we go, y equals sine x, y equals 0, x equals 0, x equals pi, and I want to revolve that around the y-axis. take a minute to sketch the region. Make sure you know what the region looks like. We'll be right back. So this is basically just the first arc of sine, right? It's bounded by the sine function, y equals 0, which is the x-axis, x equals 0, which is the left side, x equals pi, which is the right side. And I want to rotate this around the y-axis. Now, if we went around the x-axis, right? If we went around the x-axis, then I would use vertical rectangles and I would use washers, right? But because I'm going around the y-axis, I can't use vertical rectangle. I'm sorry. Since I'm going around the y-axis, right? My axis of rotation is here. I can't use washers because a washer would require my rectangle to go this way, and I can't. So instead, I leave my rectangle as vertical, and I use shells instead. So can somebody tell me how this integral is going to be set up? I mean, I just gave you the formula for it.
Top minus bottom.
Okay,
2 pi integral
from where to where?
the top minus the bottom.
What about our
Oh.
limits of integration? Where do our rectangles start and where do they stop?
0 to pi,
0 to pi. So 0 to pi.
and then sine x minus,
I agree. Sine x is the top one, minus the bottom one, which is just the ground, right?
yeah,
Which is 0. I don't need to put it there, but I'm just going to put it so you can see it, dx. But I'm missing one thing.
X.
the height.
Missing the x. I'm missing the distance from here to our rectangle, which is x. Don't forget that x. That x goes here. So basically 2 pi
Question?
integral, hold on, 0 to pi of x sine x dx. Okay, what was your question?
It's of the sine x.
You're cutting out. I couldn't hear that.
So I just want to know that how do we know it's the first half of the sine curve?
And not, what do you mean? The second half, meaning like it continues over here?
Yes.
Because we stopped x. Okay, so if I graph all of these, there's sine, right? That's your sine curve. Y equals 0 is the x-axis. X equals 0 is this vertical line, and x equals pi is that vertical line. So you've got to be between these two and between those two curves. So it's got to be this whole region.
Okay. Yeah.
Okay. Okay, are there any questions on the integral setup? 2 pi integral a to b. This right here is the distance from the axis of rotation to your rectangle, and then you have top minus bottom dx.
So
Go ahead.
I have a question. So why is the variable of x same as like sine x?
Wait,
like,
why-
because that X is representing the distance from our A to the rectangle. But sine X, the X right there is representing the graph, isn't it?
Yeah, it's representing the height of this, right?
Right.
So remember though, when I wrap that around, I create that shell of which has a thickness of dx, a height of, well, in this case, just sine x, right? And when I cut it open and lay it out, this is sine x, this thickness is dx, but this right here is the circumference of this circle, which should be, so think about your circle here, do it in red. If I just grab just that bottom point on that rectangle, wrap it around the y-axis, I create a circle. And that circle has a circumference of 2 pi times the radius. But the radius is the distance from the axis of rotation to there, which is x. You following that?
Yes.
Okay.
I think. I'm just wondering why we're not using a different variable instead of like X.
Okay, so maybe I can illustrate it this way. Maybe I can illustrate it this way. I have to start kind of with something fresh. Okay, so let's say we just go back old school style, and let's just take this line, y equals x, and let's talk about the area, not volume or anything. Let's just talk about this area. Okay. The area, what we do is we imagine filling this thing with rectangles, right? So this integral would be the integral from 1 to 2 of the function x dx, right?
Right.
Okay, so
Right.
what's happening here is that the 1 and 2, what that's doing is it's saying, where do the rectangles start? So the rectangles are going to start at 1, and they will move their way across from 1 all the way until you get to the stopping point of 2, right?
Right.
But when we say start at 1, that's an x value, right? This right here too is the x value. It's not the y value. It's just the value of x. So like if you stopped, let's say in the middle at 1.5, that rectangle has a width of dx, but the height of it is just the function's value there, which in this case would be 1.5 also. But this 1.5 right here on the x-axis is where your x is at that moment.
Okay.
But if I pick like an arbitrary rectangle and ask you, hey, where is it? All you're gonna be able to tell me is, oh, it's at x. It's some distance from the origin to there, but I can tell you it's between 1 and 2. I just can't tell you exactly where it is at the moment.
Okay.
Does that help a little bit or no?
Yes. Yes, that
Okay.
does. Thank you.
All right. We're starting this over. We're doing another problem. Okay, let's do the exact same problem. I don't want to go around the y-axis though. This time I want to go around x equals -2. Same region, different axis of rotation. Still have the sine curve. Still have this region. Still know this goes from 0 to pi. But our axis of rotation this time is back here. I have to use a vertical rectangle. I have to. I can't do a horizontal because then that sine curve is not a function of x. I mean, it's a function of x, not a function of y. So I can't go horizontally with my rectangle. So I must use shells. I have to. Now the formula I said a moment ago Where was the formula I gave you? Remember this? I boxed it. And I said, we're going to use that formula, but I left some question marks here. I left question marks because this X here is not always X. It's not accurately always X, as I'm about to illustrate in this example. But just let me work through it, okay? And then maybe you'll catch on to it. So let's start with the formula. We have 2 pi. Look, anytime you're using shells, you're going to have 2 pi. So if you write that down, you're going to get some credit, right? 0 to pi. Okay, that doesn't change. Your X value is going to vary between 0 and 2 pi. I mean, sorry, 0 and pi. I still have the top minus the bottom. I still have sine X minus 0. I'm still having a width, right? The thickness of my shells is still dx. But how about this? This right here was the radius, wasn't it? And the radius is not the distance from the y-axis to the rectangle. It's the distance from the axis of rotation to the rectangle, right? So if you know, if I've told you and hopefully convinced you that this distance is x, then what's the entire distance?
Minus 2 plus x.
Plus 2.
You add
Okay, so think of it as a
2
distance though.
2 plus
It's
x.
Plus 2.
2 plus x. So it's like a measuring tape. It's 2 plus the x. That's the total distance. And so that's what goes in front of this. Not x, but 2 plus x. And of course, that just becomes this. I keep on wanting to put 2 pi there. By the way, this problem and the one before would be done with integration by parts if you had to integrate this. But that's it. That's the integral that would give you the volume of that region wrapped around x equals -2. Any questions? So maybe I can generalize this. Maybe I can generalize this. When you're using shells, here's really what you want. You want 2 pi integral a to b. Yes, you want top minus bottom. That doesn't change. Yes, you want dx. But this right here is not always x. It's the radius, right? It's the distance from the axis of rotation to the rectangle. So I'm going to call this r subscript x. And that r sub x is always the distance from axis of rotation to the rectangle. So I'm referring to this distance right here from the axis of rotation to the rectangle. You have to always remember though that the distance from the y-axis to the rectangle is always x. So this never changes. That distance from the y-axis to the rectangle will always be x no matter what. So it's your job to figure out, using that knowledge, what the distance from that rectangle to the axis of rotation that you're given is. Let's do another one. So this same region, let's
Professor,
go.
I'm sorry, is there cases kind of like the previous example we had where instead of adding the 2 plus x, we subtract because it was shifted more towards the positive side?
Glad you asked. Yeah, let's look at this example right here.
Okay.
This example right here is going to illustrate that exact scenario. So good question. You're kind of predicting where we're heading with this. So we've now drawn this, what, this is the third or fourth time. We have this sine curve, ends at pi, here's 0. We want to wrap this region right here. We want to wrap it around the line x equals 2 pi. x equals 2 pi. So 2 pi is out here. And so our axis of rotation is out here. I know I have to use vertical rectangles, right? Because this is a function of x and there's no way to make that a function of y. So I've got to use vertical rectangles. That means I've got to use shells. I already know the formula for shells, 2 pi integral. Well, a to b is just 0 to pi because we've been through this. I know top minus bottom, sine x minus 0, dx. The only thing I really need to figure out is what's my radius. So the radius is the distance from the axis of rotation to the rectangle. That's that distance. We know the distance from the y-axis to the axis to the rectangle. We know that that's x. And we also know that the total distance from here to here is 2 pi. So what would the distance, what would our, we're calling it r subscript x. What is r subscript x?
2 pi minus x.
2 pi minus x. It's 2 pi minus x. There we go. And then what's cool about it is that if you actually pick some values of x, it makes sense. Like if x is 0, what would you get if you plug 0 into this right here for x? You get 2 pi, wouldn't you? So if we start right here at x equals 0, right there, the distance from here to here should be 2 pi. Now, by the time we get to pi, right, and we're at that last rectangle, what should the distance from here to here be? Should be pi, right? And that's what you get if you plug pi right in here. 2 pi minus pi would be pi. So this is just keeping track of that radius as you move across from 0 to pi. It just keeps track of the radius. Make sense? All right, let's look back. Let's look back now at this problem. This was a test problem, so we kind of have two choices here. I can work through this, or I can let you all work through this. We're not done though. I have more that I want to cover today. So why don't we just take a moment to sketch the region and briefly describe each of the things that you would have to do, and then I'm going to let you do that on your own. So the curves we have here are y equals the square root of x. Which looks like this. And then we have y equals 1 over x. 1 over x looks like this. And x equals 3. X equals 3 would be something like this. And the region bounded by all of them is this region right here. So if we would, let's look at A. If we wanted to wrap this around the x-axis, I'm going to use washers, right? I'm going to use a washer because I've got a vertical rectangle. I'm going to wrap it around pi times, pi integral a to b, outer radius squared minus inner radius squared. For part B, that's part A. Part A is here, right? Part B, I'm wrapping around y equals -3, which is down here. That's part B. So I'm still going to use washers, right? It's just now I'm going to have to look at what that outer and inner radius is. It's going to change a little bit.
And just add it.
And add it, yeah, in that case. And then here for C, it's up here. Y is 4, so it's above. I'm still going to use washers, right?
And subtract. So I think we can generalize it.
Yep, you'll be subtracting. And then when you get to part D, now you're going around the y-axis, right? So when I go to part D, that's around the y-axis here, I'm going to have to use shells now. And the reason I have to use shells is because it's easiest just to leave my vertical rectangles the way they are, right? Just keep using the vertical rectangle. It's working, right? And I'll use a shell around there. And then when I go x equals 5, that's over here, that's part E. I'll use shells. And then x equals -3 is over here, that's part F. I'll use shells. So this is everything in purple I'm going to do with the shells formula. Everything in orange I'm going to do in the washers formula. So I think I'll leave that to you. I'm gonna type something out here, just a little final note. If your rectangle is perpendicular to axis of rotation, you will be using which method? If your rectangle is perpendicular to the axis of rotation, you'll be using what? Washers. Okay, so that's like the orange, right? All these orange lines are perpendicular to my rectangle. Anytime your rectangle is perpendicular to your axis of rotation, you're going to be using washers. If the rectangle is parallel to axis of rotation, use shells. So in the purple cases, notice that your rectangle runs perpendicular to your axis, parallel to your axis of rotation. That's a good way to kind of remember which method you're using. Parallel, shells, right? Perpendicular, washers. Notice on this problem, I do not direct you which method to use. So when you're doing your homework for 7.2, and it tells you to wrap it around the y-axis, or, it's up to you, okay? Also, I should note this. This is something important. Section 7.3 is the section on shells, but I'm not assigning you anything out of 7.3. And so when you're doing your homework for 7.2 and you draw your regions and it asks you to wrap around the y-axis, use shells if that's what you think is the best approach. I'm just telling you that in this homework set for 7.2, the author doesn't realize that you already know shells. And what you find out if you actually were to go to 7.3 is that, well, this would have been nice to know back in 7.2. Because problems that are hard to do in 7.2 are easy to do once you have shells. So I'm just trying to illustrate that when you get doing these problems in 7.2, use whichever method you think works best. I hope that makes sense.
I have a question.
Yes.
So we've done shells with top and bottom, but does anything change if the shells were like left and right or right and left?
Well, you could have a problem like this. So watch. Let's say we go back to one of the first problems that I had today. Well, I have to make it a little different, or else it won't work. What if I do like this right here? That's not a function of x, right? And I do this right here, which is not a function of x. And I tell you to take this region right here. I didn't draw that quite the way I wanted it to. Let me. There. Okay, so let's say we have this region here. I'd have to give you the curves and stuff, but let's say we have it, and I ask you to wrap that around this, the x-axis. Can you use washers?
Yeah.
You can't use washers because to use washers means that your rectangles would have to be perpendicular, right? they would have to be perpendicular. Sorry, I'm saying perpendicular. I'm holding my hands like that, saying perpendicular. To do washers, your rectangle would have to be perpendicular, but you can't do that because these aren't functions of x, right? So that forces you to use a rectangle that's horizontal. That you can do because they're functions of y. But if you're going to wrap around the x-axis, you can't use washers this way. Then you have to use what?
Shells.
Shells. But the formula is going to be a little different. Maybe you can tell me.
So it's r sub y.
It's r sub y. Everything's just switched. It's c, it's d. It's a radius, but it depends on y. So now the distance from the y-axis to your rectangle is y, right? And it'll be not top minus bottom, it'll be right minus left. And then it'll be dy instead of dx. So do you see how it's everything that we did in the other, from the other perspective now? Yes?
And then with this, you would this be an add? You'd add the y to the function, or the radius, sorry, the height
Well,
to
in
the
this
radius.
case, if we're going to go around the x-axis, then this is just going to be y. It's just going to be y because y is the distance from here to here. Now, if that rotation line was down here, then I would have to add this much to y. So let's say that this was down here, -3. Then this right here would be 3 plus y.
Okay, I see it now.
If it was up here, let's say at, I don't know, 10, then this distance, the distance from here to here, that's your r sub y. That would be 10 take away y. So it's everything we've done just in terms of y instead of x. You're going to have to just go in and get your hands dirty on these.
So
Right.
is it okay for us to say that whenever we have the axis located on the negative side, we'll have to add that amount? And whenever it's positive, we have to subtract that number minus the r in.
Unfortunately, no, because look, what if I put my axis of rotation right there? So you're not going to add. Just because it's below it doesn't mean you're going to add. So like whatever this distance is, I don't know, maybe it's 1. Okay, maybe that's 1 from there to there. If that whole distance is y, then the distance from here to here would be y take away 1.
So it depends on the function and the way we see things, or the way we arrange it.
That's right. That's why I've said it's important for you to be able to draw it. Because if all you're going to do is say, like if you go back to that test problem, if all you're going to do is say, oh, okay, for this, there's my top, there's my bottom, and then, oh, it's y is -3, so y is -3 and below, I'm going to add 3. So, you know, that becomes dangerous because you may get the wrong formula just based upon, I know it's easy as students to look for like a pattern where you can just do that every time, right? Because then it makes it easy for you to just not worry about it. It's like, oh, okay, anytime I see this, I'm just going to always do this. If that were the case, that's the way that I would introduce it to you all. That's the way I would teach it to you. So that, but it would have to be safe in every case. And I can't teach it that way because it's not safe in every case. Not only that, okay, not only that, now I wouldn't do this to you, but not just that, but I have very conveniently always located our regions in the first quadrant, right? I mean, what if your region's down here, right? What if your region's down here and you want to rotate it around that?
It will be the opposite, but yes, we'll have to see the functions and
It's a
everything.
little more complicated, right? Because the distance, think about this. Let's say that was up here at 7, and let's say I want to rotate around that. I've got a vertical rectangle. When I talk about outer radius, yes, this distance from here to here is 7, right? But the distance from here to here is not f of x, or it's not this function. Let's say that that's the function f. It's not that function. What is it?
It's 7 minus that.
Talking about distance. So it's
Oh.
still a measurement. It's still a measurement from here to here.
Mhm.
But think about it. If this is 7, this distance cannot be that function's value. Why? What is that function's value? Is it positive or negative?
Mm,
It's below the x-axis.
Negative.
It's
Negative.
negative, isn't it?
Yeah.
So you better not put f in here, or else you're actually going to be subtracting a number from 7. So you would actually have to put negative f here, the opposite of f, so that when it spits out that negative value, you switch it back to a positive and then add it to 7. See, it can get really tricky. That's why the geometry is important. I am keeping us in the first quadrant to keep life simple, because this is a Cal 2, this is the first introduction to this. You'll notice that every problem you get in the book, you're going to be in the first quadrant. That's intentional. That's because, yes, you can handle this third quadrant, second quadrant, fourth quadrant. You can handle that, but
we
I
need to
guess
learn this first
handle that
before we
later.
actually jump. Yeah.
yeah, you handle that later. You don't even handle later like in this book. You just handle that later in your math life. If it comes up, you just have hopefully like gotten to that mental maturity, math mental maturity, that you understand exactly what I just illustrated here.
Mhm.
So geometry, the geometry of it's important. Speaking of geometry, let's go back to that test. Copy this problem. Trying to finish 7.2. This is a pretty brutal section. Brutal in terms of there's a lot in here. And I've been teaching this for a long time, and I will tell you, this concept gets people. I'll give you a moment to read that. All right, so I think the way I'd like to, before we get to this problem, I'd like for you to consider something first before we actually get into this. And we're going to do everything backwards. So let's say that I have a basketball, okay? All right, I've got this basketball. Let's say it's solid, so whatever, a solid ball. Let's just cut the bottom half off, okay? And let's just look at the top of a ball. All right, we got this top of the ball. There it is. Now, if we were to look at the base of that solid, the base of it, the bottom of it, if we were to graph the base of it, the base would look like a circle, wouldn't it? That's what the bottom of it would look like. Also, if I were to come in here with a knife and I were to cut, let's say I make a cut, right? Make a cut anywhere in that. So imagine cutting that ball. Not a good picture. If I cut that ball, right? So I cut this piece and I take it and I throw it away. And I've got like the side, this is from the side. What is this shape that is still here? What is that shape? If you look at it directly from the side.
A circle.
A half circle, right? A little semicircle. So let me restate what I'm saying. We have this solid, right? Where its base is a circle. But if you were to cut it, make a cross section of it. So take a cross section means cutting it. When you look at that cross section, you get semicircles. Right? And it wouldn't matter where I cut it. I could cut this anywhere. If I cut it anywhere and open it up, I'm going to see a semicircle, right? So clear your minds. Close your eyes. You don't have to close your eyes, but it might help. There's this solid out there, okay? You don't know that it's half of a ball, all right? there's this solid out there that when you look at its base, it's a circle. And when you look at the cross sections, they're semicircles. Do you see that it's a ball? Do you see that it's half a ball? Maybe, maybe not. Our question here is given to us backwards. They're telling us that the base of the solid region is the first arc of the sine curve. So I'll just do it below this. They're telling us that we have a solid that when you look at its base, it's just the first arc of the sine curve. So that's what the bottom of this thing looks like. And then when you take cross sections of this solid perpendicular to the x-axis, so if I make a cut through this solid like that, and I peel it and I look at it from the side, what do I see? Equilateral triangles. The question is for us to find an integral that represents the volume of that solid. This is supposed to be mind-blowing a little bit, but I have an animation that I made that's going to help, hopefully. Let me get this down here. Lots of interesting. Oh, that's all the code right there. Kind of giving it away already.
What language did you use? Is that C++?
It's C++ based. It has a lot of its own built-in functions. It's Wolfram Mathematica's, it's their language, but it's C++ based. Like you could do everything in C++ in here and it would work. It's just they have a ton of built-in functions that you can call on them at any point in time. Okay, so let me illustrate here. We've got a solid. Okay, so ignore all those little mesh lines. Just look at the blue and the blue and the red curves. The region bounded by those curves is the ground, is the bottom of this solid. And then as we take cross sections, so now I need to look at this from the side. Notice that the cross sections are equilateral triangles. No matter where I go, if I were to cut, I would see an equilateral triangle. So see how they get big, but then as you get closer to the edge, they get small. Yes? So this forms a solid. This is the solid right here. That's what it is. And the question is, what is the volume of that? Now, we didn't have to do equilateral triangles. We could have done anything. I could have done squares. So the same base, okay? The base is the intersection of those two curves, but cross sections form squares. So as you get closer to the edge, the squares get smaller. You get closer to the middle, the squares get bigger, and then they get smaller again. If you were to put all those together, you would get a solid that looks like this. So do you see all the squares on the inside of that? Okay. I don't have to use squares. I could use semicircles. That's not a semicircle. Or I could use rectangles. So here's a certain size rectangle. So rectangles inside. Yeah. Okay. That hopefully gives you some idea of what we're trying to do. Let me go through this problem. I only have 5 minutes. Let me go through this and see if you can make sense of this with me. Okay, so the first thing I do is I draw my arc of sine. That's the ground. Okay, so that is our sine function. Y equals sine x. I know that that's the first arc, so it goes from 0 to pi. And now here's the tricky part. I'm going to try and draw this in 3-dimensional space. So the way that I recommend you draw in 3-dimensional space is you draw what's called your z-axis first. Then you draw a squashed, kind of a squashed down x. Don't do like an x like this. Squash your x down. Now what I'm trying to do is draw that arc of sine over here like it's laying on the ground. Do y'all see that that's this picture in three-dimensional space laying on the ground? Now I'm going to come in here and I'm going to imagine cutting perpendicular, perpendicular to the x-axis. So I can cut anywhere I want. I'm just going to pick an arbitrary cut. So I'm just going to pick right there. Now, when I cut this, I know that the cross section looks like an equilateral triangle. So it goes up and back down. I'm going to take that triangle and I'm going to zoom in on it. Here it is. And I'm going to give it some thickness because I'm trying to find the volume of this little piece. What do you think my thickness is going to be?
dx.
Dx, okay. Can you tell me how long this side is? Can you tell me how long that base is?
Sin x.
That's just sine x. Good. It's an equilateral triangle, which means all of these are sine x, right? So I know the thickness of this. I really just need to figure out what the area of that is right there. So do we know what the area of a triangle is? Right, so I'm really just looking at that from the front. I know that that's sine x. I know that that's sine x. I know that that's sine x, but do we know that area? Well, area is 1/2 base times height. Right, area of a triangle is 1/2 base times height. But that doesn't really help me because I don't know the height of this triangle. The height is the distance from here to here. Right, that right there is h, and I'm not given that. So there is another formula for the area of a triangle that's more useful here. Maybe you've seen it, maybe you haven't. I'm sure you have if you took Cal 1. It's 1/2 AB sine theta. Y'all seen that formula before? If you haven't, let me show it to you real quick. We're going to run out of time. If you take an arbitrary triangle, does not have to be a right triangle, just an arbitrary triangle, and you call this side A, this side B, this side C. If you call this from here to here the height, and you call this angle here theta, then one formula for the area is that area is 1/2 base times height. So if I know this base, I know this height, then the area is simple to get. But if I don't know the height, I can use this formula, 1/2 AB sine theta. Now, what's really cool is to realize that where this second formula comes from. Do you see that the only thing they have that is different is that the second formula has A sine theta instead of H? Like they both have a 1/2, they both have a B, but this is A sine theta, that's H, right? So where does that come from? Well, it comes from right here, look. What is sine of theta? Look at that as a right triangle. What's sine of theta? Opposite, which is H over A, and then multiply both sides by A. So H is just A sine theta. So if you just replace that H with A sine theta, you have a new formula. But the beauty of this formula is that to find the area, all you need to know is two sides and the angle between them. Do we have two sides?
Yes.
Do we know the angle?
45.
It's equilateral. So all sides have the same length, which means all angles have the same length, and they have to add up to be 180. So 60 degrees, right? So the area of that is 1/2 sine x times sine x times sine of 60 degrees, which means, what is sine of 60 degrees? That's √3 over 2. So 1/2 sine squared x times √3 over 2. I know I'm over by a minute here, which is √3 over 4 sine squared x. All right, so the area of that triangle is √3/4 sine squared x. The thickness of that rectangle or that triangle is dx, right? So the volume of that one sliver, right, of that one piece is √3/4 sine squared x times dx. Don't worry, we'll do another one of these problems next class, but we started with the shape, we came up with the triangle, we tried to find the volume of this thing, we did, and now to get the total volume, what do? Add them up, right? All of them, integrate. So I'm gonna integrate
Yeah.
from where to where?
0 to pi.
0 to pi. And what am I integrating? That formula, whatever, √3/4 sine squared x dx. That's it, right there. That integral will give you the volume of that particular solid. See, this is not a rotation. This isn't a shell or a washer. It's completely different idea. Completely different idea. But again, it shows you the power of the integral. It allows you to add up as infinite number of things. It doesn't matter where they come from. You just have to have a formula for whatever it is. All right, we'll do more of those. I recommend that you try and do as much of the homework as you can for 7.2. This topic that I just talked about right now is in 7.2. So in the homework assignment, you look at the homework assignment. I'm going to tell you to avoid, maybe for right now, 38 and 39. Numbers 38 and 39. We've only done one example, so you can try them if you want, but I think they'll be a little tough. All right. Next class, we will do 7.4, 7.5. And then we get to start chapter 8.
Okay,
Everyone have a great day.
thanks, Professor.
You too.
You too. You have a
You too.
Thank you.
Have a good day.
You too.